Why Mars could never stay warm, the harsh truth of a desert planet. Even though Mars once held rivers that carved through valleys and lakes that filled ancient craters, the planet we see today is a cold, dry desert. This stark contrast has long puzzled scientists. How could a planet so similar to Earth end up so lifeless and barren? A new study led by Planetary scientist Edwin Kite at the University of Chicago proposes a compelling explanation, and it may finally offer answers to one of the biggest unsolved mysteries in planetary science. Mars and Earth started off with many of the same ingredients, both are rocky planets, both are rich in carbon and water, and both lie within a solar orbit that receives just enough warmth from the Sun. But while Earth evolved into a lush, life-supporting world, Mars withered into an arid wasteland. According to the researchers, the key difference lies not just in what these planets had, but in how they maintained balance over time. The new model suggests that Mars' rare periods of warmth and surface water were not steady or self-sustaining. Instead, they were triggered by the slow brightening of the Sun. As solar output gradually increased over billions of years, these pulses of solar energy may have briefly allowed water to flow across the Martian surface. But that warmth came with a hidden cost. When water is present, it speeds up chemical reactions that remove carbon dioxide from the atmosphere, locking it into rocks in the form of carbonate minerals. With Mars already lacking strong volcanic activity to replenish that carbon dioxide, the atmosphere would have thinned quickly, plunging the planet back into a deep freeze. Unlike Earth, which still has active volcanoes that slowly release carbon dioxide back into the air, Mars today is volcanically dormant. The outgassing of carbon dioxide on Mars is extremely slow. That means once the CO2 is drawn down into rocks, there's almost nothing to replace it. Even a small amount of liquid water would tip the balance, accelerating the locking away of carbon dioxide and forcing the climate to collapse back into an inhospitable state. According to the team's extensive modeling, this cycle of brief warm spells followed by tens of millions of years of desert conditions could explain why Mars has been so persistently dry. The Curiosity rover's recent discovery of carbonate-rich rocks on Mount Sharp has given this theory new strength. These rocks had been the missing piece for years. Scientists had long suspected that Mars once had a thicker atmosphere rich in carbon dioxide, but they couldn't find where the carbon had gone. If it had been pulled into rocks through the formation of carbonate minerals, just like on Earth, there should have been evidence. Now, with Curiosity uncovering such rocks at last, the puzzle may be closer to complete. Benjamin Totolo from the University of Calgary, a co-author of the study, emphasized the importance of having a rover on the ground. Remote sensing from orbit can only go so far. Understanding the mineral makeup of Martian rocks requires direct, close-up analysis. And as Curiosity continues its ascent up Mount Sharp, researchers hope to determine how widespread these carbonate deposits truly are. If they are common across the planet, it would further support the idea that Mars' atmosphere was lost not to space, but into its own crust. The study paints a picture of Mars as a planet caught in a self-defeating climate cycle. Unlike Earth, which has managed to maintain its habitability through a dynamic balance of atmospheric and geological processes, Mars appears to regulate itself in the opposite direction, toward desolation. Every time conditions improve just enough to allow liquid water, they also set off the very process that erases that habitability. In this model, habitability on Mars is not the default, it's a brief, fragile state, constantly under threat from the planet's own geology and the slow, steady increase of solar energy. While Earth developed a thermostat to keep itself mild, Mars seems to have built a one-way switch to freeze. Madison L. Turner, a postdoctoral researcher at the University of Chicago, also contributed to the study, along with experts from the University of Calgary, NASA Goddard Space Flight Center, NASA Ames, Caltech, Brown University, and the Jet Propulsion Laboratory. Together, their work reinforces a sobering insight, that habitable conditions on other planets may not just require the right starting conditions, but also the ability to maintain those conditions across billions of years. And in that sense, the true tragedy of Mars is not that it was never habitable, but that it couldn't hold on. As we continue searching the stars for life, this lesson may become central to understanding what makes a world truly livable, and what dooms it to remain forever silent.